Hi guys, we're going to introduce the operation of a dual drive conveyor belt system, which is going to be the basis for us beginning to learn about programmable logic controllers. Now, I do realize that it's quite advantageous for us to understand how a system works before we dive into creating logic for that particular system. So which is why we're just going to pick on this particular conveyor belt system so that later on we get to translate its operation into an equivalent programmable logic controlled system, because right now what we do have is essentially just a schematic which we are going to convert into an equivalent or which we have converted into an equivalent Automation Studio document, so that we're able to simulate the operation of the said control system, right? So what you're looking at before you is actually the startup sequence of this very conveyor belt system. Now you'd notice that the initialization basically starts from you having to press the start push button. Now this has to be maintained until the conveyor belt system has run through its startup sequence, because if you do release the start push button, then the system is reset. Having said that, you notice that once you press the start push button, a designated relay R1 is going to be energized, and of course at the same time we have this device which has been declared as a klaxon sound. Now this is basically just a branded siren, and then of course 60 seconds later, when a designated timer T1 picks up, the pre-start warning siren, which is the klaxon sound, is going to be deactivated, and then thereafter 5 seconds later another timer T5 is going to pick up, at which point one of the power contactors for the dual drive, which is C1, is going to be energized, and then thereafter 4 seconds later the second power contactor for the dual drive C2 is going to be energized. Now it goes without saying that at the point where T5 picked up, 30 seconds later you expect a timer T3 to pick up, and there of course the thruster brake power contactors C3 and C4 to be energized. Now this can better be seen from our equivalent document which is created in Automation Studio. Now we're going to just have to put this into simulation so that we have just a look at what we're talking about. Now if you press either the local start or the remote start, you'd notice that the local pre-start warning alarm and the remote start the remote pre-start warning alarm are going to be active. Now if you do release the start push button, you notice that the sequence is interrupted. Now this is basically just a momentary push button, but I'm going to have to latch it so that we see the sequence as it occurs, right? So you notice that you press the start push button, and then the pre-start warning alarms are active, and then thereafter at some point T1 is going to be energized, or rather T1 is going to pick up, which is now going to deactivate the pre-start warning alarms. So all we have to do is wait for like what seems like an eternity, right? And then it goes without saying that after T1 has picked up, we expect the next timer in the sequence to pick up should be T5, which only goes as far as 5 seconds, at which point the power contactor C1 is going to pick up. Okay, like so. Or rather, let's just look at the whole lot of them. Okay, so what we're saying is that C1 will be the first power contactor to pick up, and thereafter C2 is going to be the second power contactor to be energized based on the preset values of the sequence that we saw earlier. And then of course lastly will be the two thruster brakes, C3 and C4. which basically in this case are supposed to be energized 30 seconds as indicated. So there we go. So we have all the drives energized, right? So now, having done this, the only thing we're going to look at is we're going to test our system. So basically we can start with the trip limit switches. Okay, now previously we had linked a video to help us and appreciate what the trip switch was. Okay, so this is actually the pull wire operated switch. Essentially you get to pull on these wires on either side, and then it functions more like an emergency push button, right? So what we expect is that when you actuate this push button, the system is supposed to stop. Okay, so let's normalize this. So we are certain that if the pull wire operated switch, which we are referring to as the trip limit switch, is actuated, then the system will get into a faulted state. All right. The other place we would want to have this system tested is probably in the power circuit. Okay. Remember, we had inserted a residue current device. Okay. So what we're going to do is we're going to actuate the residue current device for just the first drive designated M1. All right. So to do this, we'll get into the Library Explorer under Electrotechnical NEMA. All right. Under Electrotechnical NEMA, we'll need a ground. So we need a ground, and then of course we'll need a resistive value. Can we pick one from just here or not? Let's see, apparently not. So where can we pick that? Resistors, basic, passive, and active components. We need a resistor, like so. And then we need this resistive value. Let's put it like right there. And then we need a switch. On the switches, we need a push button switch with make contact automatic return. We need this one here. When that is done, we just need to put the ground right about there. Transform, rotate right, connect it to ground, and then of course we need the switch. Of course, the only thing we need to do is we can connect any phase through the switch to ground. Okay, in this particular instance we're using the blue phase, so this is power phase 3 wire, which we are going to shunt to ground. Now we need to know the correct value to use for this resistive or rather for this resistor. So what we're going to do is we're going to know that note that the line-to-line voltage is 480 volts. Okay, so knowing that is helpful in the sense that if it's 480 for the line voltage, then the phase voltage is about 277 volts. Okay, so because we have connected this resistive value in a phase, so the phase voltage is this much, 277. And the other thing to note is that the sensitivity of the residue current device is actually 0.03 amps. Could we see this in milliamps? Okay, it's actually 30 milliamps. Okay, it's 30 milliamps if you like. So because it's 30 milliamps, let's move this out of the way maybe. Because the resistive or the sensitivity of the residue current device is 30 milliamps, the only thing we need to do now is divide the 277 by 0.03, which gives us like 9,233 ohms or 9.2 kilo ohms. So we use a lesser resistive value. So let's see, if we used 8,400, okay, what would happen? So 277, divide this by 8,400 will give us times 1,000. Okay, times 1,000 will give us 32 milliamps. So we can use 8.4 kilo ohms. Okay, so we can use 8.4 kilo ohms for this particular resistor. And then of course the only thing we need to check is the maximum voltage for this particular resistor, and we'll go for 600. Okay, we'll go for 600, and I think that's just about it. Okay, these are for the motor, to get us confused. Okay. So we can only save this now. So basically what we have done is we've rigged our system to get into a faulted state if there's a leakage. Okay, there's leakage of current to ground. So the only thing we need to do now is we need to get into simulation. Okay, we need to get into simulation, and then of course we need to prep the system for a start. So we close the disconnect, then close the individual circuit breakers, okay, for all the drives, like so. And then when that is done, we're good to get into the control circuit. And perhaps we need to look at this at the same time. So we need a parallel view, or rather a vertical view of this. So let me just pull up on the start. Okay, we don't need to look at the whole circuit, but we just need this particular one for the start. And then maybe we can just focus on drive 1. Okay, we just need to focus on this particular one, the one we have rigged for that testing. Okay, so we need to press the start, local or remote, doesn't matter, but I'm going to latch it in this case because I need for us to also look at the sequence. Okay, even though it's really not necessary, but it might be helpful that we look at the sequence, because right now we have the pre-start warning alarms active as expected. Okay, let me just pull up a little bit to the left. Okay, we have the pre-start warning sirens, as in they're active, and then at the point where these are deactivated, then we'll look at the order in which the power contactors are energized. Okay, so we're waiting for the 1 minute pre-start warning interval to elapse. Okay, so it's still active. Okay, it's done. Now we just need to look at the order of the power contactors, the order in which they are activated. So that's C1 already active, and thereafter we expect C2 to be active as well. Okay, and then after C2, then both C3 and C4 are going to be energized at the same time as expected. So now it's the time for C3 and C4 to be energized. Okay, and now we're not seeing the whole picture, but that's really not the point of this. Okay, because why? We're waiting for C3 and C4 to be energized so that the system latches. Okay, so C3, C4 coming up. Okay, that's done. So the starting sequence is fully complete, so we can unlatch our start push button, like so, because now we are latching through C4 and C3. So now the question is, well, how does the system behave when there's a leakage detected by way of the residue current device? So the only thing we need to do now is we're going to close this momentary push button, like so. And then of course you notice that C1 opens, right? The power contactor for the main drive M1 opens, and essentially the whole system is deactivated. Like all the drives are deactivated under a faulted state, like so, right? So basically that's exactly what we expect to happen under the said faulted state. For every other protective device incorporated into the sequence, because they're actually interdependent. Okay, you can't have C1 in a healthy state when C2 is in a faulted state, because it's a single system. Okay, and of course it goes without saying that the thruster brakes, the state of the thruster brakes plays a very critical role in the system, in the sense that you'd notice that the system eventually latches through the auxiliary contacts for the the thruster brakes, thruster brake 1 and thruster brake 2. So if these thruster brakes are not healthy, then the system is not going to run. Okay, so basically that's just what is expected of this system. So we've checked that the system is able to trip under a faulted state. And then, of course, I may draw your attention to just one other thing. Okay, I may draw your attention to just one other thing, that in as much as the power contactors are de-energized, the main circuit breakers are still closed. We can go about ensuring that the circuit breaker opens under residue current. Okay, under residue current detection, we may want to modify the nature of the circuit breaker that we're using. Okay, so under primary command, okay, we need a shunt release. Okay, that's what we're going to be needing. So we're going to get ourselves a shunt release like so. So let's get this. And then let's do that. A1 and A2. Clearly this is a coil, all right? So what we're going to do is we need to know what this coil is rated for. So actually it's rated for 110 volts, but clearly we're using 120 volts. Or rather, because the other way we can simplify our situation is by taking note of the fact that we already have 480 volts as a line-to-line voltage. Okay, so what we can do is this. All right, what we can do is this. We can simply just connect our coil across two phases to get ourselves a 480 volt coil. So what we're going to do is we're going to put this one here, and then of course the other phase we use the rate phase. Okay, but of course we need control over this coil. Okay, so power phase 1 wire, then power phase 3 wire, power phase 3 wire, line to line. So essentially this coil now needs to be 480 volts. Okay, so this coil needs to be rated for 480 volts. Maximum AC design voltage, we'll put this at 600. And then rated control circuit voltage, we'll put this at 480 because that's our voltage, right? So that's done. Okay. So having done this, the only thing we need now is to identify the contact that we're going to use in this particular case, and that we can get from the auxiliary, right? Because you do realize we're essentially just talking about the earth leakage. Okay, so we need to come to where the earth leakage is, like so, and then we're going to create a normally open contact group like so. And then perhaps we need to know what this voltage rating is. So maximum AC design voltage, let's just change this to 600. Okay, just to be safe. Okay, so I've changed that to 600 because there are two of them, so I don't know which of the two is which. So it doesn't hurt that I'm just going to change both of these to a rated voltage, a maximum AC design voltage of 600, so that whichever one it is of the two, it's really not going to matter either way. All right, so we're going to get this contact, and then we're going to insert it at this point. Right, let me maybe just pull this a little bit down. We're going to put our normally open auxiliary contact in the blue phase at this point. Okay, so that's now going to be our control. So now what we expect to happen is that if there's residue current detected by way of this residue current device, that this breaker is supposed to open, right? The same thing applies to every, you can do the same, you can do what we have done at this point to every other power circuit, okay? So let's get back into simulation and have a look at this once again. So we need to prep the system for a start. Close the disconnect, close the individual circuit breakers, okay? Like so. And then of course our main focus is just the power circuit for drive designation M1, which is this one here, where we have configured the testing for leakage current, okay? So now let's look at the control circuit, and then of course just initiate the start. This time we're just going to hold it down, okay? I'm going to hold it down until the system latches through C3 and C4, okay, like so. Now we can release the start push button, and then of course at this point our system is completely energized, okay? We've got our system completely energized by way of all the drives running, okay, like so. Which brings us back, or we may want to maybe reduce so that we're able to see the main circuit breaker, okay, for the drive designation M1. So the point was, if we short the blue phase to ground, okay, like so, you notice that C3, or rather C1, is open, and then of course the drive designation M1 stops. But at the same time, you notice that now the breaker designation K1 opens, okay? Unlike previously where just the power contactor is the one which was de-energized, but this time the breaker designation K1 also opens. Now, in case you're wondering why these are still running, it's because we haven't really added enough torque for them to just stop at that point. So we can fix that by way of just adding a little bit of torque to them so that they're able to stop sooner, okay? That was the only difference, but the system actually behaves in such a way that the faulted power circuit, okay, by way of, maybe in this instance we're talking about a leakage, okay, leakage current detected by the residual current device results in the breaker designation K1 opening, okay, so that it basically just isolates the whole power circuit for the network for which the fault has been detected. So that's the improvement that we can make to this circuit, and the same thing can be done to every other circuit breaker. Designation K2, K3, K4, we can add a shunt release. So our interest now is in just seeing the behavior of the system should the thruster brakes fail, okay, by way of the limit switches, okay. Now you do remember, if you go through the design of this Automation Studio project file, that we had read the limit switches to this configuration right here, okay, to this configuration right here. So the only thing we can do now is maybe look at this in association with the power circuit, okay. What's going to happen to the drives when the thruster brakes fail by way of the limit switches, okay. So what we're going to do is we're just going to open this push button, and then you'd notice that C3 this is open, C3 is still energized. Okay, so this is open, this is de-energized, and we can look at we can have a look at the limit switches. Okay, let's go up. Okay, right about there. So that's C2. Okay, there you go. So basically T2 has to time out for the system to fail. Okay, so you'd notice that what we're going to benefit out of having to translate our schematic into an equivalent Automation Studio schematic is that we not only get to see the startup sequence, but we also get to see the behavior of the system under a faulted state from either the earth leakage or the overload or failure of the thruster brake. Okay, so we've done all this testing, which gives us a pretty good idea of how the system is expected to behave. Okay, so the better thing for you to do is create this particular project file and then see how you can best play with the operation to give you different outcomes. Okay, so this basically is going to be the end result of all the videos designated as dual drive conveyor sequence control videos 1, 2, and 3. Okay, that's the intended objective, to make you understand how we created these schematics. Okay, so that will be a better point for you to start from. Understand how it works from a purely electrical control system, and thereafter go into creating the equivalent Siemens Step 7 project. So I hope this has been helpful, or rather I hope this will be helpful to you. So cheers.